we're all ready. Oh, good, we're all ready. Just to emphasize this, this is a if-then-else statement. A or B changes and A is greater than B, then Z equals A, else Z equals B. And you always get a multiplexer. I think we'll go ahead and write this down. And if then else always gives you a multiplexer as the synthesized circuit. Latch inference is a bad thing. So we'll define that. This is the inadvertent introduction of a latch into a combinational logic synthesized circuit. Now, we've looked at several examples in this lecture where our HDL code produced strictly a combinational logic circuit, AND gates, OR gates, and so forth. Latch inference takes that design, which should be only implemented in combinational logic, and the synthesized circuit has a latch in it, in addition to the combinational logic circuit. Why? Because there is a need to store values combinational logic circuits inherently can't store anything. And what causes latch inference? Poor coding. And I'm going to show you a couple of examples that lead to latch inference. Let's look at this code right here. This module has input marks, which is 4 bits, and a grade, which is 2 bits. Parameter statement, you can fail, pass, or get excellent. I do something similar like this to assign your grades, except there's really no need for that one. Okay, so let's look at the code. It says always add marks. If marks is less than 5, the grade is fail. Else if marks is between 5 and 10, greater than or equal to 5, less than 10, the grade is pass. So what if marks is equal to 12? Doesn't tell you what grade to assign. What do you notice about that code which is not good?
Excellent isn't used at all.
What?
Excellent isn't used at all.
I can't hear you.
Excellent isn't used at all. In the always.
Well, if I had put grade equals pass or fail, or pass or excellent, still would have had a problem. Incidentally, there's the synthesized circuit. We said an if then else should give me a MUX, which is implemented solely in combinational logic. There's your combinational logic, and there's 2 latches that you inferred. What is bad about that coding? What seems odd?
You shouldn't have an unhandled case for an if else.
And why do I? Why do I have an unhandled case? Looking at the way the code is written.
Because marks is a 4-bit binary value, so.
No. You notice I have if, else if. Where's the terminating else? Isn't the normal syntax if, else if, else if, else if, else? The else handles your default, right? If I had put else excellent, like there, I now have a default. It's a complete if then else, and I wind up without any latches, strictly a combinational logic circuit. Bad coding can lead to latch inference. Good coding does not. In this module, I'm bringing in a 2-bit current state. My output is zip, which is also 2 bits. I have some parameters. This kind of looks like a finite state machine, but it's not. So I have an always at the current state. Anytime the current state changes. Then in the case statement, in the case argument, I have current state. S0 and S3 zip equals 0, S1 zip equals 3, end case. What's missing?
Default.
What?
A default statement?
An equal statement?
Default.
Oh, default. I would either have to have S2 and it gives a value for zip, in which case all possible current state values will be covered. Or I need to have a default statement to cover anything not explicitly stated. Since I have not done that here, you can see the two latches on the output. Now recall that a case statement and an if-then else statement are functionally equivalent. So if you don't have either all of the states listed, all the possible values of current state, or you don't have a default, it would be equivalent to not having an else terminating an if-then else. So you get latches and forget.
So in the if then else, if we do cover all of the cases, then even without an else, we're okay. We're okay.
No, why would you do that? If, else if, else if, else if, else if. Logically, you would have an else to cover the last case.
Okay.
Put another way, if you have else ifs, you need to have an else.
Okay.
You can just have an if statement by itself. If you have two possibilities, you have to have an is, if, else. If you have multiple possibilities, then you're going to have some else if statements in there. But your terminating case, the last case you haven't covered previously, you cover with an else. Failure to do so leads to latch inference. Now, adding the default in a case statement would certainly cover all possible cases, and so you'd be fine. Come on, do something. There. Okay. This also looks like a finite state machine. It's not. Have a 2-bit input toggle, 2-bit output next toggle, and then always at toggle case statement. If toggle is 0, 1, next toggle is 1, 0. If toggle is 1, 0, next toggle is 0, 1. All possible values of toggle are not covered. Latches are inferred. I don't like this example. Better make a own example. I'm taking an example of a one-hot encoded finite state machine. And you recall in the finite state machine lecture that I would have some variable that would keep track of what state I'm in. And then there would be a case statement where I would do my state transitions. And I would have, for example, the state 0. I'm going to make this 0, so it's 3 bits. So I can have, if state is 0, 0, 1, then I do something. 0, 1, 0, do something. 1, 0, 0, do something. And I'm going to leave a space here and then put end case. Right? Now, in a one-hot encoded finite state machine with 3 states, those are the only possible legitimate state assignments. And if I coded this up like this, you get latch inference, because 111 is not covered here. Okay. So what I could do is this. Right? And now I have a complete case statement, and I wouldn't get latches inferred. Everybody agree with that? Okay. But now I want to ask a question. Does that make sense?
No.
Well, it doesn't make sense because, yeah, the default statement will preclude latch inference. But anything that would trigger that default condition is not a valid state. And in fact, those are the only valid states that I have. There is your optimal solution. Now, it looks like what I've done is I've coded up something that's going to infer latches and added a comment. But this prevents latch inference. This is not a comment. This is something called a synthesis directive. Now, by definition, a synthesis directive does not generate any circuitry. It is an instruction to the synthesizer. The syntax of it is, it must be exactly as shown, and it must be on the same line as your case statement. This is an instruction to the synthesizer that says the following: these explicit values for state that I have listed in my case statement are the only ones that will ever occur. This conceptually makes a lot more sense for a one-hot encoded finite state machine than that does. That's how you do it. Now, just as a side note, one of the design automation companies, one of the leading design automation companies is Synopsys. Synopsys is a little bit narcissistic. For their synthesizers, it's not synthesis full case, it's synopsis full case. But the full case is the synthesis directive key phrase. And this is how you would tell these synthesizers that these are the only states and you will get no lash inference by putting the synthesis directive there. Okay, so I want to briefly now go back to a construct that we talked about briefly before. Okay, this construct implies some sort of priority. And that is based on the order in which conditions are checked. And let me give you an example here. Let's look at this code here. This has got a case X in there, so the any bid positions that have a don't care are ignored. And in this case, if toggle has a 1 in the least significant bit, next toggle is going to be 0, 1, 0, and so forth. There is a default statement in here to cover all possible cases that you have not listed above. Now, this case statement is functionally equivalent to this code here. In fact, I'm even going to do that. If you look at the if statement and you look at the case statement, what is the first thing I check in the if statement? The least significant bit, toggle 0. The next thing I check is the next least significant bit and then the most significant bit. Okay? So there was an order based on how I had set up the if then else statement, checking the least significant bit to the most, then the next least significant, then the most significant. The question is, What if I know that these cases that are listed are mutually exclusive? If one of them is true, another one cannot be true. That would be the case, for example, in a one-hot encoded finite state machine. I'm only going to have one bit that's going to be a logic 1, and the rest are all going to be logic 0. Rather than having this default, oh, and incidentally, there's the synthesized circuit. It's all combinational logic. You have the default statement in there. So you didn't have latch inference. You had a terminating else condition in the if then else, so it's a complete if then else. No latch inference, combinational logic circuit only. But the default kind of doesn't make sense. But we'll leave it in there. If you know that each one of these possible case argument values are mutually exclusive, you can use this synthesis directive parallel under bar case. And that says these are all mutually exclusive. And of course, for synopsis, this would be synopsis parallel case. By making these mutually exclusive, notice the effect on the if then else statement. Those all become independent if statements. And you wind up with a much simpler combinational logic circuit. These are just double inverters. So this could equivalently be a wire, and a single OR gate, which was a simpler circuit than what you had before. So again, this is a synthesis directive. It's an instruction only to the synthesizer. It must be in that form, and it must be on the same line as your case statement. There's one last situation that can lead to latch inference. And that is a variable used before given a value. And as a simple example, let's suppose I declare a 4-bit variable temp, and then I have always add clock or temp. If clock temp equals Y. Remember that this is going to execute at time t equals 0, and there's nothing in here that shows I've given temp a value, but it's in a event list. There's going to be a latch inferred in this circuit, and the reason why is, remember, the purpose of the latch is you haven't given me all the values, so I may have to store the previous value. So since you didn't tell me what temp is, I've got to have a latch to store what its previous value is, whatever that might be. So that's your last situation leading to latch inference. Loop statements. Here I have a